Dr. Pratik Jain with us. So Pratik Jain is a research scientist at Google Research India, where he leads the ML optimization team. He obtained his PhD from UT Austin and BTech from IIT Kanpur. He has conducted foundational research in areas of large-scale and non-convex optimization and resource-constrained machine learning. Pratik Jain regularly serves on the senior PC of top ML conferences as an action editor for JMLR and CMODs. He has also won multiple Best Paper awards, including the 2020 Best Paper by IEEE Signal Processing Society. Pratik also received the Young Alumnus Award from IIT Kanpur and the ACM India Early Career Research Award. So it's an honor to have on to you, Pratik.
Thanks so much, Gagan, for the generous introduction, and thank you to you and Shalab sir for inviting me here. And thank you all for attending this talk. This has been a wonderful workshop, although I could not attend a big part of it because of some other prior commitments. So in this talk, I want to sort of discuss this one line of work that we are pursuing, where we want to use the statistical methods for online decision making under uncertainty. And we want to sort of bring in ideas from this recommendation system and collaborative filtering that is sort of a passion for me. Like I've been working in that area for almost 10, 12 years, along with these ideas from reinforcement learning and online learning around explore plus versus exploit. This work mostly has been driven by Sumibrata Pal, who was a postdoc with us and now is a researcher at Adobe Research, as well as Arun Sugala and Karthikeyan Shanmugam, who are researchers in our team at Google Research. I'm just giving the talk. I haven't done most of the work here. So this is sort of a very rough outline of the talk. So I'll first start with why we believe that in this online decision making, we need collaboration, what we mean by collaboration there. And then I'll talk about a couple of specific methods that we've designed for a specific setting, and talk about some simple practical algorithms that we've designed based on this and how they have been able to make significant impact in some real problems as well, like real world applications as well. And then I'll conclude with some future directions that I believe are quite exciting. Throughout the talk, feel free to stop me and ask questions. The main purpose of the talk is mainly to just sort of convey this big sort of area of problems that I believe needs to be solved. Like there are multiple sort of opportunities there. I would say the algorithms that we have are just barely scratching surface. They are not really solving the problem access. So there is a lot of scope for further innovation, for sort of making much deeper inroads and giving more deeper insights into the problem. Okay. So we know that in general in any online system or something, we need to sort of make decision making under uncertainty. So for example, if you are on YouTube, YouTube sort of makes its decision that this user has come to my homepage, what videos they might be interested in, right? Now, one option is to sort of, say that, okay, I know that this user, let's say in past watched a deep learning video. So I just sort of, show them on their homepage, just show 50 other deep learning videos that they might be interested in, but that might not be very useful because at that point of time, maybe the user was interested in deep learning, but maybe they would want to explore areas around it, right? Or maybe they have some other interests that have not been reflected in the history so far. So we would want to sort of, do much better decision making under uncertainty here. We have some understanding of the user, but a lot we don't know, and we want to do much better here, right? So multi-arm bandit and contextual bandit and more general RL have been sort of very good tools to understand these problems. So multi-arm bandit sort of models this problem very easily, very nicely in a very intuitive manner. It says that suppose I have a user, I have let's say some number of items or arms in the bandit literature, and I don't know which item the user will like, right? A priori, I might have some limited understanding of the user based on whatever they have in the past, let's say, liked about certain items, but I don't know about full picture. So what I need to do is I will need to do a bunch of exploration. I will need to explore each of these items maybe at least once, and then understand that what is the user's preference, right? And that means that the amount of exploration, and that's why amount of regret or cost I have to pay, will be somewhat along the lines of the number of items that I have in the system, right? So that's great, and this we cannot do any better than this as well, right? But in most of the online systems, we are not in this kind of setting, right? We don't have one single user. we have millions or billions of users in many cases, right? So then for each user, then how do I figure out what they like, what they don't like, and what items maybe I want to recommend them or show them, right? So if we apply standard bandit optimization for each of the users separately, that is, we'll say that, okay, although I have billion users, I will treat them as billion independent multi-arm bandit optimization problems. In that case, how much exploration, like total exploration, total cost I will need to pay in some sense, that cost will be something of this order, right? I will need to explore number of items into number of users. And imagine at Google or Netflix level, this can be very costly because if let's say there is a irrelevant useless item that I'm showing to the user, I am wasting my watch time opportunity, my monetization opportunity, etc., etc. So there's a significant cost to be paid, and that's why if you propose this solution to an engineering team, they will immediately say no. This is not possible. Like we cannot do this much of exploration, pay this much of cost to get an unbiased understanding of the user. We need better solutions, right? So one approach that we have is to bring in some sort of a structure in this problem, right? So what is this structure based on? Well, we know that recommendation systems and collaborative filtering have been around now for decades, and they have worked very well. And there, the basic idea is very simple. The idea is that all the users are not completely independent or not completely different from each other. Sorry. So generally, you can identify some data structure or some commonalities between the users. So for example, if let's say the user is from certain demographic and have certain kind of interactions, etc., with the system, maybe they are more likely to like certain kind of items, right? So maybe if the users are some PhD students in IISc fourth year, maybe they would like some particular type of movies, right? So that I think that commonality is what is used very nicely by your standard collaborative filtering or recommendation system kind of methods. We want to see if the similar thing can be now done in this bandit optimization as well, so that we don't completely bias our system. So one very simple thing is basically assuming some sort of cluster structure over the users and items. So what I mean is that suppose I can cluster my users in some number of clusters, let's say a very small number of clusters. So I might have billion users, but maybe let's say I have only 1,000 clusters of users. And within each cluster, then how user prefers certain items is fixed. That is, if there are two users within the same cluster, then their preference for items is more or less same. Here we have for simplicity, we have said that the preference is exactly the same. We can relax this requirement, but it should be more or less the same. Now, one more better generalization of this clustering kind of thing would be what's called low rank structure. That is, if I think of this user by item preference or reward matrix, then this reward matrix or preference matrix can be decomposed into a very low rank matrix, which essentially means that each user can be represented by a few latent variables. Each item can be represented by a few latent variables. And the preference of a user for an item is based on the inner product between those latent variables of the user and item. Okay. But for now, for simplicity, let's just consider this very, very simple cluster structure. And this cluster structure is not even this very simple structure is not completely out of our figment of our imagination, in data sets like the movie length data set and all. People have been able to show that similar clustering of users and items can be done. But as I said, a more powerful structure would be to assume some low rank structure on these users and items. So, so what has been done in this piece so far, right? So one line of work obviously is this standard collaborative filtering or standard recommendation system kind of things. There you have some user item preferences that you have already recorded in your system. That is, maybe the system already knows that user 1 likes deep learning video, user 2 likes topology videos, user 3 likes category 3 videos, category 3 videos, right? So that information is already present in the system. You say that I will just try to do some kind of collaborative filtering or low rank matrix completion there. And that gives me an embedding of the user and item. And based on that, I will do my recommendation. So that's one standard way of doing it. as I'm saying, like, that is not a great way, because this system will then be very biased by the existing set of information I have, right? That is, if let's say a user has watched the deep learning videos, I will imagine that this user is in deep learning cluster and always show them deep learning videos, which is not great, right? I might want to explore a little bit around deep learning, maybe show them some sort of like, linear learning or regression kind of videos as well. So that this sort of system will not be doing. Okay. So offline, like offline or like this biased recommendation system or collaborative filtering methods, they have that issue. They are practical but have significant bias issue. Then when we look at sort of more sort of online learning based techniques, there are a couple of key works that have been sort of proposed in the area. So there is this very nice work by Mallard and Manner, where we are assuming that the user's reward structure or cluster information is already available. Maybe by looking at the demographics of the user or by through some other means, I can sort of already priorly say that these set of users are similar to each other, can be clustered together, and so on. So in that case, then they can sort of get optimal algorithm. Optimal algorithm in sense of, say, an algorithm that has good regret bound. Right? Then there is this another line of work started by Claudio Gentile, which says that, okay, I will want to work in a setting where I don't know the user's membership in a cluster, because many times that information is not available in Prairie. Like, the demographics of the user or some other features tend to be very, very weak indicator of how the user will interact with the system. Right? So they said that, okay, suppose we don't want to assume that structure, then what can we do? So they have some interesting algorithms, but unfortunately they are far away from being having like an optimal cost. In fact, like the cost is still sort of dependent on the number of users and number of items in a sort of worse manner there. So so like it's a great start, but it is not really sort of making like solving the problem in the at least in the key terms that we want. In this work, we have a couple of algorithms, a particular algorithm called lattice, and there's a simpler version of the algorithm that we are calling greedy algorithm, where we are able to follow the same sort of recipe. That is, we are not assuming a priori clustership membership, like information about clustership membership of the users and items. And even then, we can get an algorithm which is almost as good as we can hope for. There are still some critical terms in that, bound and that regret that we have, which needs to be optimized. But I would say that the big terms, like the key terms that we wanted to do well on, those we are able to solve fairly well by this algorithm. So I'll present that in a bit. Any questions so far? Overall, I hope I've sold you on the problem itself, that the problem is quite important. Okay. Yeah.
I just want to make sure that your clusters and rewards don't change.
Yeah.
Even though they are unknown, but you presume them to be.
Great point. So right now we are assuming that the cluster structure or the underlying low rank structure is fixed. If it is changing, we can, like, if it is slowly changing, then we can deal with it. Or if it is changing according to a very simple dynamics, then we can try to estimate it. But that's a great sort of direction. Like, we haven't done much of a work there. Yeah.
So with this work, right, we focus more on exposing, I mean, in the context of recommendation systems, they focus more on exposing them to exploratory items that they haven't interacted with before.
Precisely. And the focus also, like I'll show you the algorithm, it will become more clear, but the focus also is in to make sure that this exploration can be done in a collaborative fashion, right? If I am treating each user as a separate and then do separate exploration, that's very costly. So I want to figure out a way where maybe a cluster of users can sort of explore some items together. And I can say that, oh, I showed them item 1, they didn't like them. So user 2, who is very similar to user 1, I should not show that item to them.
Just to add a bit of context to the question, right, we're doing, but not with bandits, for personalization. And what we typically found is that, at least in the Walmart setting, right, most of the recommendations actually, the success we have is with showing them repeat items, not exploratory items. But again, it completely depends on the domain in which you're working on. For instance, for Netflix, for instance, I want exploratory items, things that I haven't seen before. But in some other domain, repetition is more key. actually getting the final result. I just want to.
So that's a great point, and so that adds one more nuance here. So which I sort of I had sort of separate, which is that the user many times is not just coming to the system. Like I was talking about YouTube homepage because there it maps very nicely. But many times user will also issue some query or give some more signal about what things they are looking for, right? So if let's say they come on Walmart side and they say that okay, show me diapers, right? They're like they would most likely be comfortable whatever diapers they have been using for their baby, so they would want that to be repeated. But on Walmart side, they might also come and say that show me red dresses, right? So there they probably wouldn't want to see the dress that was shown earlier. They would want a lot more exploration there. So there is additional component which is user's intent captured through query or some other signals, and that should also then dictate how much exploration we want to do. In this framework, we can do that, but for the purpose of this talk, we will, yeah. Any other questions? All right. So yeah, so this is what I was going to come to that. In practice, this is we are not doing this very simple recommendation system world where user is fixed and they don't have any intent, and items are also fixed and don't have any intent associated with them. Generally, what happens is there are some sort of user features and user input. There's some item features like item product, title, cost of the item, etc., etc. And then, like in most of the current recommendation system, what happens is that you then take these user features, pass it through some deep neural network, get a user embedding, pass the item through some sort of network, get an item embedding, and then try to do some sort of similarity learning on top of them, right? And the point is that this system will also be again biased by whatever is being shown right now. So in this general system, ideally, we would want to bring in this exploration thing, right? That is, can we have this exploration which is collaborative and is also contextual? That is based on the context we can do it. Again, some of the algorithms that we are talking about can be extended in this world, but for the purpose of the talk, I would discuss. Okay, so let's talk about like a precise setting that we are studying in collaborative multi-arm bandits. So the setting is that we have the bunch of users in our system. Again, there are in practice, there are a few more nuances here because your users might not be fixed. You might have a new users coming in, some users dropping out. Let's ignore all that for now. And suppose what happens is that we have these rounds that are happening. That is, in each round, suppose you have to give some item to the user. Again, it need not be like this. We can split the round itself in the way that a user comes to the system and I have to recommend an item. So that might be a definition of a round. But for simplicity, let's assume that in one round, we are giving one preference to, or one item, suggesting one item to all the users, right? Not same item, but different set of items. But to all the users, we are suggesting some items. This is then the definition of rounds. And what we want to do is we want to, at each step, we are accruing reward, right? So what is the reward? Reward is that when user U is being recommended some item J, then do they like that item J or not, right? And that can be based on some underlying true reward matrix plus some sort of noise that might be there in the system. That is, sometimes user really like an item, but because they might be in a hurry or they might have some other distraction, they might not have clicked or liked that item or not purchased that item. And what we want to do is we want to optimize this regret, right? We want to say that, okay, if I already knew the preference for each user a priori, then I would have recommended that best item for that user. So compared to that best item, how badly I am doing in terms of the total reward, right? That is, I'm getting reward at each cycle based on what I recommended, right? Plus of some noise. And I want to say that that reward should be as high as possible compared to the best item that I could have recommended to the user in hindsight. Right? Okay. So standard definition, yeah.
No, I'm just saying that there will be a reason why you are going for subclassing analysis.
It just makes life easy from analysis point of view. I think it can be extended to at least noise that has bounded force moment, but it's just like it makes analysis more and more hard.
That's why this question. This great definition assuming that the user has a unique, there is a unique object for which he or she gives the highest reward, and they would prefer to be recommended that same object for all
time steps. Yeah. Great question. Yeah. So right now, that is what will happen in this setting. We have a sort of another setting, a sort of more generalized setting, where we have some kind of blocking kind of thing. That is, with some probability, I want to see the second best item rather than the best item. And then if I have seen two items, then with some probability, I would want to see the third best item rather than the first item. So that can be modeled. So we call that as blocking collaborative filtering. And there again, like, we have done very initial work there. Like there are a lot more sort of, practical, considerations that can be put there and sort of, made to work. Yeah.
Only the system to guarantee the cross-selling and upselling.
Cross-selling, upselling, for now, we are not bothered about. You can do similar modeling, cross-selling kind of thing, where you can say that, okay, for this item, what are other items I want to recommend? So you can sort of, design that online system, but for now, we are just talking about user to item recommendations. M is the number of rounds, which is not a great. Sorry, M is the number of users. Sorry, M is the number of users. Sorry, yeah.
Assuming that the reward matrix is fixed.
Yeah. For now, we are assuming that the reward matrix is fixed, and the sub-Gaussian noise is also IID. So it is stationary. But yeah, as we discussed briefly, like ideally we would want to make it at least slowly varying, and that's a very sort of interesting direction to pursue.
Each round you get a sample for each user.
Well, like again, this is not a hard testing. We can, yeah. For in this one we did that.
So the rounds for the same number of samples for
all users.
So you can treat them.
We can treat them equally. In principle, like same analysis applies even if, let's say, each round you're getting only one user and you're recommending one item to them. Like that can be done, but for now, we are. Yeah.
By cluster.
So the cluster structure is already assumed in the true reward matrix. So that's already assumed. Any other question? All right. So we have a very, very simple greedy algorithm for this problem, which is sort of probably the first algorithm that somebody will think, which is that, okay, in the initial phase, I will just do exploration. And after that, I will just do exploitation, right? That is the initial phase. I will just sort of show some maybe random items to each of the user. Based on that, get some sort of understanding of their preferences. And then I will just do exploitation. That is, after that, like once I understand their preference, I will just, based on my estimation of their preference, I will just keep on showing them the best item according to the preference matrix. So this is the greedy algorithm. Again, I can play with it. One key thing here is that how do I know, like in the exploration phase, how would I know how would I estimate their underlying preference matrix? For that, we can use this thing called low rank matrix completion, or collaborative filtering, in other words. Let me take a very quick 2-minute detour of what is low rank matrix completion or this collaborative filtering. So here the idea is that you have some users, some items, some of the information between user and item is available in terms of their preference. So here maybe the preference might be rating of a user for a given movie or item from 1 to 5, but this can be 0, 1, it can be continuous number, whatever we want, right? And the assumption is that the underlying matrix, like a rating matrix or underlying preference matrix, is low rank. So if it is low rank, right? So if I have n items and n users, I'm keeping notation here, sorry for that. And if the underlying rank or the cluster, number of clusters is k, then the number of free variables in this system is only mk plus nk, right? Although when I want to complete this matrix, the number of outputs that I'm giving is m times n, but the number of free variables is only mk plus nk. So if k is much, much smaller than m and n, that is, if k is much, much smaller than the number of users and number of items, then the number of free variables is just sort of linear in m and n, whereas here it was sort of quadratic. Like the total number of output that I'm giving is quadratic. Right? So, I can try to solve this problem by saying that, okay, I have some observations that I denote by this set omega. of the true matrix, and I want to find this matrix X, which is low rank, because that I know is the structure I want to satisfy. So that on the known entries, the estimated matrix is very close to the observed matrix, like on the known entries, right? So this problem, unfortunately, is not easily solvable because rank constraint is not convex. The problem itself is actually NP hard in general, even to approximate within logarithmic factors actually. But there are like a couple of approaches that are very popular. There is one approach called nuclear norm or trace norm based optimization, and another technique that we have worked on for quite a bit called automatic minimization. Idea behind nuclear norm minimization is very easy. You can think of rank of a matrix as some sort of L0 norm of its singular values. That is, if I take matrix X, write its singular value decomposition, then its rank is essentially number of non-zeros in that singular number of non-zero singular values. So it's a L0 norm kind of thing. We know that the tightest convex relaxation of that L0 norm is L1 norm. That is, rather than looking at number of non-zeros in the singular value, I can take a summation of the singular values, and that's a very good sort of convex approximation at least. So based on that, I can get a convex problem to solve. So now this problem that I have is a convex problem, can be solved, and you can obtain some very interesting bounds. There was this very seminal work by Candace and Greg long in 2007, which started this whole field and like showed that under certain assumptions, you can indeed recover the underlying matrix M by observing only about M plus N log n samples. That is, although the number of outputs I'm giving is M times N, but by looking at only M plus N into a log n samples, I'm able to sort of recover the underlying matrix exactly. So that was sort of a pretty interesting result that they proved. This trace norm optimization is a little bit tricky. Like, if you have millions of users and millions of items, it's hard to scale. So we did this line of work called alternative minimization, where we didn't do this convex approximation, but instead directly proposed to solve the low rank like the non-convex optimization problem. That is, we said that, okay, if X is rank K, we can always write it as a U times V transpose, where U is a very tall matrix, V is a very sort of, wide matrix, and or V transpose is a wide matrix. And then we can alternate between U and V. That is, we can fix U and optimize for V. It's a simple linear regression problem, can be optimized very easily by standard linear regression methods. Then fix V and optimize for U. Again, it can be done very easily. So the optimization algorithm is very easy to implement. In general, this optimization algorithm might not do anything. That is, it might get stuck on some very poor, like not even local minimum on saddle points, or it might not attempt converge actually in many cases. But what we were able to show was that under the conditions where this trace norm based method can be shown to converge to the optimal solution, we can show that under pretty much the same conditions, this alternative minimization method, which is much easier to implement, much simpler to understand, can also converge to the same optimal algorithm. So that was sort of one of the big results that we had proven out. So we can use any of these techniques for the purpose of our work. Like right now in the greedy algorithm or subsequent algorithm that we'll be designing, we are assuming matrix completion or this collaborative filtering as a black box. You can use maybe trace norm based method or alternative matching method or some other methods. All we need is a good solution that is able to solve this problem well. And once we have solved this problem well, we have estimated this reward matrix up to some extent, then we will commit and just do exploitation. That is, for each user, we'll be figuring out that what is the best item for them and always recommend them, or let's say, right? So, although this algorithm seems like, sort of very naive and useless, and sort of non-practical, but still, at least from theory point of view, we can show that this works reasonably well. That is, what we are able to show is that its regret scales something like this, right? So here, there are two things. So one very important thing is that the regret scales as number of items by number of users. That is, if let's say the number of users is very large, then what we are saying is that the regret is independent of the number of items. Like I might have 1 million items in the system, doesn't matter. If I have a large number of users and suppose the underlying rank or the number of clusters is small, then we are not really paying in terms of number of items. We are sort of, we have almost constant sort of regret there. And in terms of number of rounds or number of time steps we are taking, There it is scaling as number of rounds to the power 2 by 3. Right? So roughly, big things are covered here nicely, right? That is, it is sublinear in the number of rounds. That is, if I have infinite many rounds, the regret will go to 0. And the regret doesn't scale linearly with the number of items, which means that for each user, I don't have to explore all the items. This roughly sort of says that on an average for a user, the number of item that I need to explore is essentially number of items by number of users. So average exploration per user is very little. Yeah.
Just to make sure I understand, when you say greedy algorithm, does it refer to the fact that after you do matrix completion, you are greedy thereafter?
We are greedy after that, yeah. And there are a few assumptions obviously here to make this matrix completion work, but yeah.
How do you define the exploration?
So here we are roughly exploring for about t to power 2 by 3, and that's how it is. Like for greedy algorithm, you can show that that's one of the best we can do.
The K is hidden in the icons.
K is hidden here. So it is not really items by users, it is items by users into K. So the total exploration, like if you combine all the users, the total exploration has to be number of clusters into number of items, which sort of makes sense, right? That is for, like in my system, I have basically the amount of information that I have is number of clusters, and for each cluster, we have some sort of preference for items. So the amount of information is K into number of items. And we are saying that if we can explore that much, we are good to go. We have understood the system, and that's why we are able to do recommendation so very confidently.
So you say here that instead of to take this the bandit for number of users times number of items.
Yeah. Yeah. So if you apply the standard bandit methods, then this factor will be root of rounds, and this would be bad. This will be basically number of users plus number of items, root of them. So we want to sort of get rid of that number of items term on its own. We need the number of items by number of users kind of term.
Why you got 1 plus is negative?
Probably
the numerator because someone.
Yeah, this is so because in our regret we had this 1 by n term. That's why, like in the regret definition, we normalize by the number of users. So that's why. But roughly, like what it is saying is that the total exploration across all the users that we are doing is of the order of number of items, or number of items into number of clusters. Okay. Any other questions about this result? So, in terms of analysis, like even this analysis was quite tricky because unfortunately matrix completion itself is a pretty hard non-convex optimization problem. So it requires a bunch of assumptions like, the matrix should be almost square, it has some incoherence condition, condition number condition and whatnot. So we had to overcome that by bringing some new techniques like doing some sort of random partitioning of the whole system, etc. I will not go into detail here, like those are more of technicality, but it can be solved basically. Now we have this another method that we call lattice, which is able to do better than this sort of suboptimal result, but it's definitely a lot more involved. So this algorithm is able to give a regret bound of this type. Like it is basically root of number of items by number of users. Again, a number of clusters is hidden there. Although it's not like linear, it is actually cubic on that, but it's there. And it is like you have like root number of rounds now. Yeah.
The previous thing is very slow, but
yeah.
The assume matrix completion is not exactly
no, so that we cannot assume, right? Because there is a Gaussian noise and we are taking some number of samples. So yeah, so those also you can extend. You can extend that to have noise. So alternate minimization as well as alternate minimization, their results are somewhat weaker, but the trace norm based method, there even if you have noise, you can show that you can estimate things pretty accurately. And in fact, here we needed the estimation to be very accurate. Well, I mean, it needs to be accurate, but we needed
this problem does not have a behind.
So that we are assuming that we are solving that matrix completion problem to the optima. So if let's say you have trace norm based method, it's a precise optimization problem. We are assuming that you are reaching the optima of that. Like it's a convex optimization problem, we are reaching optima. But the thing is, like you can show that that problem is like restricted, strongly convex. So getting to the true optima, at least in terms of rates, is not that bad. Like you can get to an epsilon approximate solution in about log 1 or epsilon equations. So if let's say epsilon is set to be whatever value you want, that will be fine. So there is that hidden term, but for now we are ignoring that.
You can adjust that with the number of transports.
Yeah, so that more can be done, but for now we have ignored it. As I was saying, like there's more complications here because matrix completion generally, like because these are like sort of spectral methods, we typically get Frobenius norm or L2 norm kind of bounds. But here, because once we commit, for each user we are recommending one item, right? So we need like a much stronger L infinity point of bounds. That is, for each entry in the matrix, we want a strong approximation. So it can be done with that same like trace norm as well as actually alternating minimization, but it requires a lot more. Any other question? All right. Yeah, so this lattice algorithm that we have designed, this can do optimally in terms of number of items, users, and rounds. So these big terms that are there, it is able to get it correctly. Right? And we observe that in practice also, like well, practice is somewhat weak term here. Like these are some simulations on this Netflix and movie lens data. There also what we observe is that as you increase the number of rounds, the regret for lattice is much smaller than your applying very standard alternating minimization where you're not worrying about the bias as well as actually UCB kind of methods. UCB in this particular case is very bad because it is not able to do any collaboration. All right. So while like this result seems like we have solved the problem, as I was saying, far from that. Like so, this is just sort of showing that big terms you can get correctly, but there are a lot of sort of subtle things that are still missing, right? So one is the number of dependence on the number of clusters. So right now our dependency is something like CQ in the regret bound, whereas the optimal dependency should be root C. So if the number of clusters is very large, this might start to come into picture. So ideally we want to improve that. Another sort of more critical thing to me is, well, I mean, this we can extend. That is, we can say that rather than each user cluster having the same, like for every user in a cluster having exactly the same preference for all the items, we can allow for a little bit of deviation there. Right? But I feel like there are like multiple issues. So we want this deviation to be somewhat larger without changing maybe the rank preference. So that's one. Second thing is that we need to assume things like that the underlying reward matrix is what's called incoherent. And that also is and has good condition number and all. And that's also not a great assumption. If we can avoid it, we would want to avoid it. And that falls back to because the machinery that we are using here is low rank matrix completion. Right? That is, we are saying that, okay, in the initial, we'll do some exploration and then we will run matrix completion. So instead of matrix completion, if we can use some other machinery, maybe a clustering based machine, like pure vanilla, like a clustering kind of algorithms, maybe we can get rid of some of those assumptions and do much better. So that I feel would be probably like a better algorithm to do. So there are a bunch of sort of issues like that are hidden under the rug here. So what is the approach for lattice? Like how are we able to get this nice optimal rate in terms of the big terms here? So there are a couple of key algorithmic ideas, right? So one is that we want to reduce the problem to low rank matrix completion roughly. So that's one idea. And another is to use this phase elimination kind of approach, which is also popular in multi-arm bandits. Although they are like in multi-arm bandit, they are much better algorithms like Thompson sampling and UCB and all. But phase elimination is also a reasonable method for multi-arm bandit. The thing is that multi-arm bandit, like phase elimination method, is much better suited at least for this collaborative online learning kind of problem because we can separate out some estimation phase from exploration phase. Because right now that's the best we can do, like from matrix completion point of view. So like phase elimination for multi-arm bandit is like extremely simple idea. What you do is in phase one, you say that I will want to estimate each item's reward up to a precision of let's say half. items that I have in the system, so that I can estimate like reward of each item. Like item which is like say almost one away from the current best estimate, I know that I can throw it away, right? Because I've estimated those items. So I know that if I am throwing something beyond reward, that item can never be. So in after phase 1, I will eliminate some number of requirement. That is, now for the remaining arms, I will want to run but up to precision of 1/4. And if there is anything that is throw them out and so on. So I will then again throw them out and to a small number of arms that I am being sampling for and estimation for. So this is very nice from collaborative filtering point of view, because there are completely combining the estimation with exploration here. We are first doing estimation. Okay, so like phase elimination for MABs, it's very, very simple analysis. Let's assume that the reward has the noise. Item 1 is optimal. This item 1, mu I is the actual reward of item I. Item 1 is the best item. Then delta I is how far mu 1 is from mu I. Right? For each of those times, because that's the regret I have. So I will be able to get like the very simple like all the items are also active, similar to phase elimination. Everything is active initially, and then what we do entire reward matrix to get a rough estimate of the top items, essentially, right? So what I do is I will run matrix completion on this entire matrix, but for a very crude precision. Once I do that, then what I do is I will so matrix completion will give me embedding of each of the user, each of the item. I can cluster those embeddings, right? So that way I will have, let's say, let's say here the number of clusters is 2. So I will have, let's say, 2 clusters for my users, right? And then what I do is I need to sort of estimate that in each cluster, there will be some items which are not good. They are like, I should be able to sort of say that these items are not going to be preferable for these users. So if I can do that, then I can eliminate those items in each cluster and just focus on smaller subnetworks. So there is like a little bit of math going on here, how we do it, but roughly what we are doing in each phase is we want to sort of do clustering of users. After I do clustering, based on like approximation in terms of reward matrix estimation, I will be able to remove some set of items from each of the cluster. So now I have these 2 independent problems, and they have a smaller number of items and smaller number of users. And I will just repeat this thing. That is, I will say that I will keep on going to a more and more homogeneous set of users, more and more homogeneous set of items, and I will be running my estimation like this, running collaborative filtering or recommendation on that smaller and smaller set. That's what roughly the algorithm will be. So I'll just ignore the analysis part, but that's roughly what the algorithm will keep on converging. So we are solving now this collaborative filtering on a smaller set of users and items, which intuitively also makes sense. That is, initially you are doing some exploration, very little amount of that exploration to understand which users are similar to each other, which items are similar to each other, group them, remove some items that can be easily ignored in that group, and then again run the same thing and just keep on sort of making these groups smaller and smaller and more complex. Any question about this rough algorithm, maybe? Yeah.
Question. So when you are doing this clustering,
Yeah.
you have to make sure that you don't make mistakes, right? Because it looks like you're only sub-clustering thereafter.
Yeah.
So how do you keep track of that?
That's a great point. So that's why this precision becomes very critical, right? Like we are saying that based on matrix completion, we will be about at a delta precision in terms of estimating the actual reward, right? And now we are throwing away things which are, let's say, at reward of 2 delta away. So by that, we are able to guarantee that we are not throwing away important items or true best items in any of these elimination cases. And that's a great point, and that I feel is one of the sort of, bad part of the algorithm also, because it is then very, very conservative. Like otherwise we could have eliminated a lot more items much more quickly. So if there was a way to sort of eliminate some item and then bring it back later on, it would have been much better. But for now, we don't know any, like how to do it.
Doing a hard clustering, like maybe some probability of
that you can do, but I think it's still, I'm not sure if that will help a whole lot, because ultimately like those means are still sitting, and like if we are doing something, like if you don't have a method that can bring things back in in a more intelligent manner, later on it will be a problem. Yeah. Any other questions about the algorithm itself? Okay, so yeah. So I'll ignore the proof and all. Let me talk about one very simple, so this algorithm is great, but a bit harder to implement in practice many times. So we have sort of come up with a technique which is somewhat in the middle between the pure greedy and pure like phase elimination kind of method. So this method is actually like a little bit more practical. We've implemented it and we have got some interesting results. So what we do is the following. Initially, we do some exploration. We get some sort of estimation of the matrix, and then actually it is somewhat similar to what Gugan was saying. That is based on the rewards that we are getting for each of the item user item pair. For each user, we will then normalize all the items like based on some sort of softmax, right? And then that becomes a probability distribution of which items I want to recommend for that user for now, right? So what we do is based on this probability distribution, I will for this user I will sample some item based on this distribution, show it to the user, get feedback, etc. And then again run it like sort of in an iterative fashion. So like this is sort of the overall picture. We have some information about user item preference. We run some sort of standard recommendation algorithm. We get a full estimate of user item pair. We run row-wise softmax that gives us a probability vector. We do sampling from that probability vector to then augment the data and then again run this whole thing. So this is a very simple method, almost same as the greedy method. I don't think we can show anything better than the T to power 2 by 3 rate right now, but it works like a charm in practice so far. So I think there's more to be done. So why do I say that it works well? Well, we have applied it in this one very interesting problem of maternal health, sort of healthcare, which is project led by AI for Social Good team at Google Research. So that's a sister team. So this team is working with a NGO called Arman, where what they do is for expecting mothers, they want to sort of educate them about various things like what they can expect during various time of the pregnancy and what nutrition they should be taking, etc., etc. So what they do is they give some sort of initial material to these mothers for them to follow, and then they try to call these mothers so that they can reinforce that material, right? Now you can imagine that the workforce that they will have to call versus the number of mothers would definitely be very disproportionate. So they need to call like, mothers that they think are like really at risk of dropping out from the program, right? So they need to figure out like, who is the best person to call to. Like if I have to make one call, who is the best person to make that call to? So this problem again, like, we have tried to sort of, model through the same collaborative filtering kind of, or online collaborative filtering kind of thing, where we are saying that you have these mothers, and then we have some actions like, call, not call, and a couple of other actions that we have. And then we are trying to sort of say that what is the reward of taking a certain action for a user. And then what we are saying is these mothers can also be in some sense clustered because they have like, similar demographics. So for example, if there are some working mothers, they might sort of drop off if you're not calling them in evening. So they are like, those kind of clusterings that can naturally happen. We don't know those a priori. Those are sort of just guesstimates. So we have mothers on one side, actions on the other side, and then we apply this algorithm. And what we are observing, again, like, no need to go in detail of all these graphs, but roughly what we are saying is that on an average, we can reduce the number of calls by almost 50% by using this kind of technique over using like a standard, like, UCB kind of method. So if you are applying standard UCB method, you would like, you have to make like almost 2x calls. So this is based on offline data. We are getting more online evaluations. Okay, so what happened here? So because it is reinforcement learning workshop, let me give one sort of slide picture of how these ideas can also be applied in reinforcement learning world. So imagine that you have a MDP. You have a bunch of users. Let's say all the users share the same sort of state, action, transition matrix. But the reward function for each user that has some sort of low rank structure between them, right? So in that case, can we then like, come up with some method where we can obtain the optimal policy, but the regret of the optimal policy or the number of samples that we need for that optimal policy should scale as users plus number of states into actions rather than multiplications of that. And by using similar-ish ideas, like collaborative exploration ideas, we are able to get like, same kind of thing here. That's a sort of separate line work, but yeah. Okay, so I'm almost out of time. So, like, the main takeaway is that these modern recommendation system or modern, like, decision-making systems, they are not like a single user system. There are millions of users. You cannot hope to sort of, model all the users by one single model, right? So you would want to capture nuances between those users, but at the same time, they have commonalities that can be captured through low-rank structure or clustering structure, etc. So we want to come up with methods like, these bandit style or online learning or reinforcement learning style methods that can do collaboration in a sort of very effective manner. And here, sort of, we have formulated this sort of first set of problems in this domain, come up with some very simple methods like greedy method and phase elimination methods that are able to solve problem up to some extent, but there are many more interesting problems remaining. As I was saying, like, we can sort of, extend some of these techniques. So low rank structure, for this blocking constraint kind of structure there. We don't want to repeat the same item again and again. We want to recommend some other item, but a lot more needs to be done. That's all.
So thanks a lot for this wonderful talk. So now the forum is open for questions. Please go ahead.
So in offline data, like, we had to do. Yeah. So I mean, we use the standard trick that is, we do some sort of, resampling these, like, based on our current policy, we would have some distribution on the actions, and then we are sort of, renormalizing it and try to fix this problem. Yeah, so but we would have some probability distribution for the item that was done, right? And we are saying that that will do some kind of reading and compute it. So it is not the greatest evaluation, and that's why we would want to do more sort of precise online evaluation, and that's sort of what we thought of. Yeah.
How are the clusters being determined during the patent?
So basically, matrix completion gives you a embedding of the user like a very low rank embedding of the user and the item, right? So we are taking the embedding of the user and running some sort of clustering method on it. So in practice, we would be doing something like k-means. For the purpose of the paper, it is very sort of hard method. That is, we are saying that like you can pick, let's say, one random item, so user in a cluster, and then everything within certain threshold, every user within certain threshold is within that group. Otherwise, they are one. So, and because we are doing matrix compression pretty well, generally we are able to ensure.
So the matrix completion algorithm is done on the entire matrix or within within the clusters, like some matrix?
In phase 0, it's on the entire matrix. And then as we are going along the phases, we'll be running them on each of the sub-matrix. Because for each user cluster, there will be some items cluster. And only on that sub-matrix will be running it. And that's why it becomes more and more efficient as we go along the rounds. Because the number of items and users that we have to explore now becomes more and more.
So, the top thing, do not care about the data. There is some stamp release. Because you are online data, you are not actually following. So, I think that there will try all the
I think that also we have done. I have to check with the people like how it is, but that's a great point. Like generally, that.
Offline data is for data. We take this entire data.
I think maybe that sort of analysis is in that. I will check.
Are there any more questions?
One, I know based on, we think that adding bonus to industry, because whatever data you see is dependent on the information. So,
Yeah. So bonuses in what sense?
like base definition is complete as good as use the data we have seen.
Yeah.
And industry. So if you your exploration, I use bonus based methods.
Then I have to think through like the main issue that generally face, at least from theoretical point of view. In practice, it might help. From theory point of view, these matrix completion algorithms are very rigid. Like basically, each sample has to appear with some fixed probability IID. Like that's the only setting where they work. So that makes it a bit more difficult to do any correlation between different phases or. But in practice, you are right. Like it might.
Are you assuming all the items to be independent or are you considering some correlation? Like, for example, users who might not be in the same cluster, the users who like let's items might also like item 7. So are you assuming some type of correlation?
So for items also, we are assuming some sort of clustering. That would be sort of.
So maybe in the interest of time, we can take other questions offline. As I said, during lunchtime, we request all the speakers to be, as depending on how much time permits, to be available to the students who can perhaps come forward and get their questions clarified. So let us now take this opportunity to thank Pratik Jain for this excellent talk.